Frequency policy. Frequency autoregressive visuomotor policy with continuous tokens. Robot learning requires efficient, precise manipulation. We propose effective action representation as key, questioning whether time domain sequences are optimal or alternatives should be explored. Our focus, hierarchical modeling for course-defined generation. In low-dimensional pushing tasks, results are revealing. 10% low-frequency components achieved 43% success, 20% reached 70%, 50% attained 87%. Full-spectrum use caused slight performance decline. This demonstrates action signals compressibility. Low frequencies contain essential motion information, while excess high frequencies introduce noise. For 26DOF dexterous manipulation, low-frequency components alone fail. Success requires gradual inclusion of higher frequencies, with full spectrum needed for completion. This validates frequency domain's potential for hierarchical modeling. Complex tasks demand high-frequency precision, and as embodied intelligence advances, frequency domain modeling better supports hierarchical learning. We confirmed these findings through energy heat maps and success rate curves, demonstrating that different tasks depend distinctly on various frequency components. Having established frequency domain as an effective action representation supporting hierarchical modeling, we consider that both frequency and original action spaces are continuous. Our investigation into continuous versus discrete modeling shows continuous attribute methods, diffusion policy and frequency policy, significantly outperform discrete-based models, CARP and BET. The frequency policy framework encompasses training and inference phases. During training, observations are encoded while expert actions undergo discrete cosine transform to frequency domain. A frequency index K is stochastically sampled, with corresponding coefficients conditionally reconstructed via inverse DCT to yield K-level actions. Concurrently, an adaptive masking ratio is determined based on the frequency index. The model processes masked observations and reconstructed actions through encoder-decoder architecture, with diffusion serving as a continuous tokenizer preserving action continuity. For inference, observations are encoded while action tokens are initialized to 0 with complete masking. The model iteratively predicts actions at progressively higher frequency levels guided by the current index. Partially reconstructed tokens undergo encoder-decoder processing to generate continuous latent codes conditioning the diffusion sampler's predictions. These predictions are transformed via DCT into frequency domain and refined through IDCT to the next frequency tier. The masking ratio decreases adaptively, facilitating course-defined progression until complete action sequence reconstruction. In real-world experiments, we tested frequency policy in a dynamic human-robot handover task. Video evidence confirms its real-time responsiveness. The system used a Kinect RGBD camera with foundation pose for 6D pose estimation, sampling 4096 mesh points to create 5-frame historical point clouds with shadow hand states as inputs, predicting 3 future frames. Combining precise pose estimation with efficient inference enabled stable 25 FPS operation, proving frequency policy's value for real-time robot control.